dear students. So, we will continue our discussion on understanding the magnetic mirroring, which helps us to confine plasma. So, this is the geometry that we have taken, in which the magnetic field lines are converging into the positive z axis, and by drawing the same radius at two different points, we have realized the strength of the magnetic field at these 2 points will be same, which means there is a gradient in this direction, which is what we have written here. The magnetic field gradient is parallel to the magnetic field itself, right. So, that means there is an invisible component of magnetic field along the r direction, yeah, right. So, how do we get it? I mean, so let us say if we have to understand the magnetic field, the fundamental law that magnetic field obeys is del dot B is equals to 0. The divergence of magnetic field is 0. So, cylindrical coordinates, right. So, we have a field like this, something like this. This is the r cap direction, this is the z cap direction. So, the magnetic field now has an axial component and a transfer component. So, this magnetic r component is not visible directly, but you have to see carefully, you will realize how the r component is existing, right. So, using del dot B is equals to 0, why I have used del dot B is equals to 0? Because any configuration of magnetic field has to obey this. So, now the geometries, we have BR, we have B phi, and we have Bz. Of course, the B phi component is outright 0, we do not see anything here. Bz is, of course, we have started with a non-zero Bz component. Now, Br is something which seems to be hidden in the plain sight, but if Br is 0 or not has to be explained by this simple equation, right. So, if I expand this divergence, I will be able to write 1 by r dou by dou r of r Br plus dou Bz by dou z is equals to 0. So, I have not written the phi component of the divergence equation, because B phi is 0 or change in B phi along phi is also 0 at a value of r, right. Now, just look at this equation carefully. If this equation has to be true, there is no doubt that del dot B has to be 0, because by the fundamental nature of the magnetic field, it has to be satisfied. So, if it has to be 0, the way the magnetic field is changing with respect to z, why is the magnetic field changing with respect to z? Because you have considered a configuration like this, in which the magnetic field is converging into a smaller space as it travels towards the z axis, right. That means there is a positive gradient in the magnetic field in this direction, right. So, if this dou Bz by dou z is positive, or if it exists, it has to create this additional term. This additional term has to compensate this so as to make the sum as 0. So, this is cause and effect kind of a thing. So, since you have created a magnetic field like this, it invariably produces a magnetic field component along r, which again just goes ahead and tries to nullify dou Bz by dou z, just so that divergence becomes 0, right. So, now this equation also gives us how we can get Br, the invisible component Br, in terms of the other things. Let us say, for instance, I will write the entire divergence, okay, for the sake of clarity, rather than just saying something will be 0 outright. Dou by dou r of r Br plus 1 by r dou B phi by dou phi plus dou Bz by dou z is equals to 0. Now, if you are wondering how did I write this equation, from where did I write this equation, you have to refer to some basic vector algebra in which, or you can just go to this electrodynamics book by Griffiths, where you can see all the relevant formula of vector calculus are given in the first page itself, where the divergence is written in all the coordinates. If you write the divergence in, if you write the del operator in Cartesian coordinates, it will be like this: dou by dou x along I cap plus dou by dou y along j cap plus dou by dou z along k cap. So, similarly, the del operator can be written in cylindrical coordinates or in the spherical polar coordinates, and those relevant formulae you can find anywhere. I have just used them here. Del dot b is equals to 0, and also using the fact that b is now defined as br, b phi and bz. Right. Now, dou b phi by dou phi, you understand what is dou b phi by dou phi? You take the cross section, you fix the value of r, let us say, you fix any desired value of r. If you draw this 360-degree arc from that point, these different points will indicate different values of phi angles, right? And we have created a magnetic field which is such that along this loci of points, the magnetic field's b phi component will remain a constant. So, this derivative outright becomes 0. What we are left with is 1 by r dou by dou r of r br plus dou bz by dou z is equals to 0. What does it mean? If at all the magnetic field has to have a gradient along z axis, then this component, this term should be non-zero. If at all this dou bz by dou z has to be 0, it is impossible to have the divergence of gradient to be equal to 0 without this term being non-zero. Okay. So, we can write simply r br is minus integral, this derivative goes the other side, becomes an integral, is 0 to r dou bz by dou z times dr. So, simple vector, simple calculus, where I am just trying to separate br, or r br is integral of r becomes r square by 2, which is minus r square by 2 times dou bz by dou z plus a constant of integration, right. So, how do you get this constant? Let us say for all values of r, including r is equals to 0. This expression is valid for all values of r. What is the meaning of this expression? Why is the radial component of the magnetic field so impossible to see in the plane sight? Because we have taken a configuration in which the magnetic field is just along the z axis. The radial component is something which comes into existence only because of the convergence of the magnetic field. Otherwise, this component would not exist, right. That is the meaning of this expression, by the way. So, this expression is valid for, so this is valid for all values of r, obviously, right. So, let us say we take r is equals to 0. Is this valid? When r is equals to 0, everything becomes 0, but the constant C1. So, C1 survives. So, how do you get this? So, this is very trivial. We never discuss these sort of things, but let us say if you are still wondering, so if I substitute r is equal to 0, I will get this 0 is equal to 0 plus C1, which means C1 is 0. So, that means the constant, we do not have to worry about the constant, and we will go ahead and write r BR is minus r square by 2 dou Bz by dou Z, or BR is minus dou Bz by dou Z into r by 2. Where did this minus come from? This minus came from the fact that the divergence has to be 0. That is why this term, when taken to the other side, gave us a minus. Right. Now we have BR, but most importantly, BR seems to be just dependent on the magnetic field Bz and the way it changes with Z, and it also seems to be dependent on R. You see, larger the R, larger will be the magnitude of B, but of course there is a minus. So, these two things will not increase in the same direction, rather they are correlated in the opposite directions. Right. So, this is the beauty of the geometry, that it spoke for itself in terms of this simple mathematics. Right. So, what can we say? We can say that the magnetic field increases linearly with respect to r. So, I can now safely write the direction for this as r cap. Right. So, as you go along the geometry like this, as you go along this, with increasing values of r, you are bound to get larger magnitudes of magnetic field. So, you go back to this cylindrical geometry you see here. I will just draw it rather than just something like this, right. So, in this, with increasing values of r, you will get more and more stronger magnetic fields. That is the meaning of this. Right. Now, having done all this, now the magnetic field configuration has slightly changed. So, ideally we expected this to be 0, 0, Bz, because we thought the magnetic field only has the Z component, and coupled it with del B, right. Having added this del B into the configuration has now made it as BR 0 Bz. You see, that is the change that it has got along, right. So, this is BR non-zero just because del B exists. Now, let us try to go back to our equation of motion. What is the equation of motion? M d square x by dt square is, let us say, I will not use x, rather I will use r, is q times v cross p, right. So, v is Vr, V phi, Vz, and B is Br, B phi, Bz. So, you can write Vr, V phi, Vz. Since the particle has no limitation, it can have a velocity along any direction, but the magnetic field has some limitations, where we have restricted the magnetic field to have an indirect radial component, a 0 phi component, and a direct z component. So, we can write the force as q times v cross p, or we can write Fx using this, we can write Fx as q times V phi Bz minus Vz Br, Fy as q times minus Vr Bz plus Vz Br, Fz q times Vr B phi minus V phi Br. Right. So, let us say we call this equation as 1, 2 and 3. So, B phi is 0, right. So, this term becomes outright 0 and this term also becomes 0. Now, how many terms we have? We have 1, 2, 3, 4. What are these? These are the components of Lorentz force. This is the components of Lorentz force. Now, let us put this in contrast to the magnetic field only along z axis without any convergence or without any gradient, where we have Fx as q times Vy Bz and Fy is minus q times Vx Bz and Fz is simply 0. So, this actually we have obtained at the beginning of the last class. So, if you are wondering what are these equations are valid for a particle which is in a magnetic field along one direction. So, this magnetic field is not changing its magnitude along a particular direction, but whereas the configuration shown in equations 1, 2 and 3 has a magnetic field along z axis, also has a gradient along the z axis. That is why they are different. But the contrasting difference between these two equations is that what is the type of motion that the particle executes under this force? Can you make a guess? Fx and Fy, if you put Fx and Fy, you will realize that it will give you something like Vx square plus Vy square is something like in a measure of RL square. It should be x square plus y square is equals to RL square if the center is at the origin. But the point is Fx and Fy, the force components Fx and Fy will just make the particle gyrate along the axis, along the magnetic field line. It will gyrate along the magnetic field line. So, it is not going anywhere, you see, it is just gyrating. If you put an electric field, the particle will move along the direction of electric field. But Fz on the other side, Fz is simply 0. So, the magnetic field is not able to move the particle along the z axis, Fz is 0, right. But what is it doing? It is just executing a circular motion which is defined in the xy plane. You see, Fx and Fy are non-zero and they seem to be dependent on the components of velocity which are Vy and Vx. But you compare this to equation 1, 2 and 3. Fx and Fy will still be continuing to give circular motion, no doubt, but Fz seems to be in the opposite direction, you see. Let us write Fz. So, Fz is equals to minus q V phi Br. We know Br as minus half R dou Bz by dou z. So, Fz is minus q V phi R by 2 dou Bz by dou z. So, this 1 minus comes because of the charge q, let us say. Now, if this is your z direction, let us say if the particle is gyrating like this velocity component becomes v parallel and this velocity component is v perpendicular. So, v perpendicular has the x and y components vx square plus vy square, whereas v parallel is simply vz square. So, we can safely assume that the r and phi components will still continue to give circular motion. So, fz v phi is plus minus v perpendicular depending on the direction of gyration. So, fz can be written as minus plus, because there is a minus, plus minus becomes minus plus after multiplying with minus, becomes half qv perpendicular RL dou bz by dou z. Substituting something that we know already, half q v perpendicular by omega dou bz by dou z. Again, RL is equals to m v perpendicular by qb, or m by qb is 1 by omega c, or omega c is equals to qb by m. Right. So, we can write fz is minus plus half mv perpendicular square by b dou bz by dou z, right. So, this force Fz seems to be dependent on this mv perpendicular by 2b. We have discovered that this is nothing but the magnetic moment in the beginning of the last class. So, Fz becomes minus mu dou bz by dou z. So, at this point, what have we learnt? We just have taken some configuration of magnetic field, and in that configuration we realized the particle will experience an additional force along the negative z axis. So, this non-zero force along the z axis is responsible for trapping of the plasma particle in a given magnetic field or in a given configuration of magnetic field, which we call as the bottle configuration, okay, something like this. Okay. We will stop here and we will continue the remaining part of the magnetic mirroring in the next class.